Alright, this is section 5.6, a fundamental theorem of calculus. Now let's think about before whenever we had this integral. The definite integral from 1 to 2 of x squared dx. We were looking for the area under the curve of x squared from say 1 to 2. So we were looking at this area right here. Now the way we did this before was we either broke this section into rectangles and estimated the area, or we used a formula from geometry to come up with that. In this section, what we're going to do is we're going to take this definite integral, we're going to look at how to evaluate it straightforward by using a fundamental theorem of calculus. Alright, let's look at a fundamental theorem of calculus first. Part 1 anyway. Part 1 of the fundamental theorem of calculus says if lowercase f is continuous on a closed interval ab and uppercase f is any antiderivative of lowercase f on ab, then the integral from a to b of f of x dx is equal to capital F of b minus capital F of a. What does that mean? Here's what this basically means. If you're evaluating this definite integral, what you do is you find an antiderivative first of all, which we call f, and you evaluate that antiderivative of your upper limit of integration, then you subtract from it your antiderivative evaluated lower limit of integration. So how do you integrate this again? Antiderivative evaluated at upper limit minus antiderivative evaluated lower limit. Let's practice. All right. Let's suppose we have evaluate for our first example. The integral from 4 to 5 of x squared dx. And let's use our fundamental theorem of calculus, part 1 here. Alright, so how do we do this? It said, let's find an antiderivative of this integrand. An antiderivative of the integrand is x cubed over 3. Now what we're going to do now that we have limits of integration is we're going to put those in here like this with a bar, 4 to 5. Alright, so here is my antiderivative. What do? I evaluated at 5, so we have 5 cubed over 3, minus my antiderivative at 4, so 4 cubed over 3. Well, 5 cubed is 125 over 3, minus 4 cubed is 64 over 3. Alright, keep my denominator 3. What's 125 minus 64? That's what, 61 over 3? And I cannot simplify that, so that is my answer. Now some of y'all are thinking, when I took the antiderivative here, I didn't put plus c. Well, let's see what happens whenever we put plus c. We really don't need it, but let's see why. Suppose I have the same integral from 4 to 5 of x squared dx. And I go ahead and put that plus c because I'm used to doing it. So to evaluate this, find an antiderivative of x squared. So we're going to say that's x cubed over 3 plus c. Now I want to evaluate it from 4 to 5. From 4 to 5. So let's see, that's 5 cubed over 3 plus c if I evaluate this at 5, minus my antiderivative here evaluated at 4. So 4 cubed over 3 plus c. Put that on the screen. So that gives me 125 over 3 plus c. What if I distribute the negative here? I get 64 over 3 becomes negative minus c. Now what happens if you have plus c and minus c? They zero out. And what are you left with? 125 over 3 minus 64 over 3. And what did we say that is? 61 over 3. So you can see, if we put in a plus c, what's going to happen anyway whenever I evaluate it at my limits of integration? It's going to end up zeroing out. So I can just save time and not put the plus c because I know that.